In this demonstration, we're looking at stationary transverse waves in a string. The string is a bungee cord that's attached to an inverted speaker. And when I put a signal in the speaker vibrates like this, causing this end of the string to vibrate. That pulse then travels down the string to the pulley and then reflects back. The string is put under tension by this string by hanging weight on its end. Let's put in a very low frequency pulse now and see what we get. In this case, we have one antinode in the middle. This is the lowest possible frequency in which this particular string can vibrate. It has a node at this end and a node right in front of this. Now let's increase the frequency and see what happens. We increase the frequency just enough, we get a pattern in which there is one node in the middle and where the wavelength is equal to the length of the string. The distance between two nodes is always half of a wavelength. So we have 1/2 of a wavelength and 1/2 of a wavelength for a total wavelength. Increasing the frequency even more now. We skipped one. There we have two nodes, a node here and a node here, and any node in the middle, so we have 3/2 of a wavelength. Here's a good pattern. We have a node here, a node here, and a node here. So we have 1, 2, 3, 4/2 of a wavelength. Since this is half of a wavelength, that means the distance from here to here is one wavelength. So we have 4/2 or 2 wavelengths in this string. The velocity of this pulse depends upon the type of string and the tension, or how tightly it's stretched. The frequency depends upon the frequency of the pulse we put in the speaker here, and the wavelength then is going to be governed by the length of the string and the number of nodes and antinodes.